I know this is a very sad day for everyone, but this is your last lecture for the semester. We're almost there. Today is going to be pretty action-packed. We got some Yo Mama jokes and a bunch of relativity. So let's just dive right in. Imagine you are in an elevator. Now, if you're standing in this elevator and it's not accelerating, right? It's either moving at a constant velocity or it's just not moving. Then you're going to experience a certain amount of gravitational force pushing down, right? And so the bottom of the elevator is going to push up on you an equal amount, and that's just going to be how it is. However, if the elevator starts to move from rest, right, if it accelerates upwards, then it's going to accelerate you upwards, and it's going to make you feel heavier, right? Now, we've all felt this before. When the elevator starts to accelerate upwards, you get this sinking feeling, right? Like gravity increases. Thus, it is impossible to distinguish the difference between accelerating and experiencing a force. This, of course, presumes that you don't know that your frame of reference is accelerating or not, blah, blah, blah. But Einstein stated this is basically true for all phenomena and not just gravity. This gives rise to this funny thing we call the principle of equivalence, and that goes a little something like this. Imagine you're in a spaceship, right? Moving at relativistic velocity, but also accelerating still. Now let's say that there's a window here and a beam of light comes in through the window, right? Now, if you're accelerating, is this going to just go straight through here? If you're moving at a constant velocity, it's going to look like it kind of goes that way, right? In your frame of reference, even though what's actually happening is the ship is moving farther up, right? And so by the time this beam gets to the other side, it's going to look like it's moved or tilted towards the back. However, if you're accelerating, it's not just going to move towards the back, it's going to move further and further back, causing it to go in a parabolic arc. Crazy, right? Thus, the beam should appear to curve towards the back of the ship. Now, this is exactly equivalent to gravity also bending light, because if you remember, this thing we call the principle of equivalence states that an acceleration is indistinguishable from a force, because they're both going to cause accelerations, right? So, gravity bends light. And that means that if we take the path, the trajectory of this light, we can very clearly see that if there's like a star here or something, and there's like a black hole here, then the light from the star will bend around the gravity well of the black hole, and it's going to look like the star is actually over here, whereas it's actually behind the black hole. Crazy, right? Anyway, this is called gravitational lensing, and I've included a diagram of what that actually looks like. In any case, this gives rise to one of my favorite Yo Mama jokes, and that is, Yo Mama's so fat you can see what's behind her. In any case, the acceleration is indistinguishable from gravity, and also the greater gravity, or the acceleration, the slower time moves. It's like getting closer to the speed of light. Now, if you're trying to escape from a very strong gravity well, like a black hole or something, if you're trying to get out, then time would move slower for you, your frequency would decrease, your wavelength would increase, and any light that you emitted would get shifted towards the long wavelength or red side of the electromagnetic spectrum. This causes what we call a gravitational redshift. And this is equivalent to energy being sort of removed from the light by intense gravity. Now, this gives rise to another one of my favorite Yo Mama jokes, and that is, Yo Mama's so fat her toenails aren't painted, they're red-shifted. Hey. My favorite actual Yo Mama joke is Yo Mama's so stupid I told her to do the robot, now R2-D2 has crabs. But we're not going to go there. In any case, we know from Johannes Kepler that the orbits of the ellipses, or the orbits of the planets around the sun, are ellipses. Which, if you remember, an ellipse is if you took two focal points and then you summed up all of the points where the distance from these 2 points added up to a constant, you would have an ellipse, right? So these 2 lengths add up to a constant that's the same as these 2 lengths, the same as these 2, the same as these 2, and so on. That's what an ellipse is. And of course, this is highly elongated. Most of the planet's elliptical orbits are only maybe a couple percent different from a perfect circle, right? The Earth's actual orbit is only about 1% different from a perfect circle, so it's probably better than how I've drawn it here now. In any case, we know that the orbits of the planets are elliptical. However, it was Einstein who realized that the direction that these ellipses are facing, right, because ellipses, they have this 2 focal point configuration, right, and so they have one axis that's greater, it's called the major axis, and this smaller one here called the minor axis. And the direction that the major axis points changes over the course of time. We call that apsidal precession. And the planet Mercury is the closest and therefore precesses the most. I've included a diagram of it, but essentially we wanted to think about how apsidal precession goes. So if the sun's here, right, this would be like one orbit, but it doesn't just go like this, it goes right, and continues to rotate. But why is it that we say that matter warps the curvature of space-time? Well, consider, if you will, a disk that is rotating at relativistic speed. Now, if you placed a meter stick on the edge of the disk, perpendicular to the radius of the disk, right, and this thing is rotating this way, then what's going to happen? Well, it's got a relativistic speed tangential to this axis, right? It's got some relativistic speed, and so it should suffer some length contraction. And if you're an observer standing out here somewhere, it's going to look like this meter stick is smaller than a meter, right? Thus, the ratio between the diameter and the circumference is no longer the number pi, right? That is no longer true. We also stated earlier that due to the principle of equivalence, an acceleration is indistinguishable from gravity, or any force for that matter. Thus, in the presence of a strong gravitational field, the geometry of space-time becomes what we call non-Euclidean, or not flat with straight lines, right? You can't just draw some grid out here and say that this point is this distance from this other point. It's not that easy, right? Now, if you drew, let's say, a triangle on a flat surface, you would know that all 3 of these angles add up to 180 degrees. If you drew a triangle on, say, the surface of a sphere, right, this would have to bow out, bow out, bow out. And so these interior angles would always be greater than 180 degrees. And if you drew a triangle on this other funny thing we call a saddle surface, it would be less, because it would curve inward, right, instead of outward, like on the surface of a projecting sphere, right? Now, if you wanted to look at the shortest distance in between any 2 points on the surface of a sphere, right, let's say from, New York to Tokyo or whatever, you have to go along this funny route called the Great Circle Route, or the geodesic, which is actually the shortest distance in between these 2 points along the surface of the sphere. Now, since gravity warps the curvature of space-time around massive objects, and light always takes the shortest time path to get in between one point and the other, 3 observers on the 3 closest terrestrial planets to the Sun may see light bent in the region of space-time around the star. Thus, the total angles made up in between, let's say we've got this situation. So here's the Earth, Here's Mercury, here's Venus, and here's the Earth, right? Here's the Sun, and this is the closest planet, this is the next closest planet, and this is the third closest planet, right? Let's just fill these in a little bit. And this one's the farthest. Now, because they're moving, presumably at relativistic speeds, right? It would be much more pronounced at relativistic speeds. This triangle would similarly have angles that would be greater than 180 degrees, because space-time is curved positively around massive gravity wells like stars and black holes and what have you. It can be helpful to picture space-time as like a rubber sheet, or a waterbed for those of us who don't have good imaginations. And so let's say that you had like some rubber sheet and you took a bowling ball and you dropped it into the rubber sheet. Well, at that point, what's going to happen? The rubber sheet is going to sag, right? Now let's say that in this depression where there's this bowling ball, right, this saggy part, if you rolled a marble into it, it could roll around it. And if there was no friction in between the rubber sheet and the marble could essentially just roll around in that depression kind of forever, right? Now, if the bowling ball is a star, that makes the marble a planet. And the path of the marble going around the bowling ball, because there's no friction in between a planet and space where there's no matter, that means that path that the marble is taking is what we call an orbit. Now, I talked a whole lot of shit about this book and the author over the course of the semester, but by far the biggest problem that I have with this author is that he states gravity research up to maybe 2014 at best, and probably long before that, and doesn't say anything about this. LIGO, the Laser Interferometer Gravitational Observatory, where we proved once and for all that gravity waves are real. We set up, two huge Michelson interferometers, one in Livingston, Louisiana, and the other in Hanford, Washington. And I've included a picture of the one, I think, in Washington in the diagram, or excuse me, on the chapter 36 lecture page. In any case, those have huge interferometers with very, very long lengths. Each of them are about 4 kilometers of a side, and it's like that so that if a gravity wave goes into the Earth, we should be able to measure the interference pattern on the detector of the waves recombining, right, as the path lengths change. Now, the author calls gravity waves difficult to measure, but that's a bit like saying the distance from here to the end of the universe is far. It's a tremendous, crazy understatement. So we detected a gravity wave from a 40 or so solar mass black hole, or a black hole about 40 times the mass of the Sun, combining with another 30 or so mass black hole on September 14th in 2015, and the energy that it released was incredibly high. Now, if you took that gravity energy and made it into an equivalent burst of light, for that brief instant that it was emitted, it would be brighter than all of the stars in the universe combined. Something like more than a solar luminosity in total of energy, of pure matter being converted into energy. Just one solar mass just turning into light. But how is it that we were able to detect these things, these gravity waves? Well, imagine, if you will, a hula hoop. Okay? Now let's say a gravity wave that's oscillating this way goes through the hula hoop. What's that going to do? Well, it's going to stretch the hula hoop out this way, which is going to collapse the sides in this way. And then as it passes through, the system is going to equilibrate, right? And it's going to sort of accordion itself a little bit as it settles and stabilizes into its normal configuration. Why is that significant? Well, if now this hula hoop that we're talking about is our interferometer, right? Here's our beam splitter, here's our mirror, here's our other mirror, down here is our detector, right? This is our laser source where the light goes in and then splits. And if a gravity wave goes through the Earth, then we'll get a changing interference pattern here at the detector, right? And this is how we detected gravity waves. Long story short, it has a very, very signature kind of signal, because as these two things get closer and closer to each other, they're eventually going to leave gravity waves and then combine into one large mass, right? There's now a black hole of about 70 solar masses. Actually, it's closer to about 69 because one solar mass was sent off as a gravity wave through the universe. But as they approach each other and become one single singularity, it gives off a very distinct pattern. Now, detecting that pattern, at some great distance, light years and light years away from us, is not easy. It's equivalent to trying to hear somebody whispering next to you if there's a jet engine from 10 feet from both of you. It's not easy, but fortunately one of the few things that we are good at as a species is signal processing. And so by looking for this telltale pattern, we were able to prove that gravity waves exist. And so Einstein was right. And about 100 years after he predicted that we would find them, we did. Long story short, relativity is the only theory that accurately describes gravity. It is the only theory that gives us reproducible results, the only one that actually has any useful predictions on how gravity works. The problem with that, one of the major problems that we have in science, and especially in physics, is that the other three forces, not gravity, we're talking about the weak and strong nuclear force and the electromagnetic force, are much better described by quantum mechanics. Now, there was a fundamental irreconcilability in between quantum mechanics and relativity, because relativity is predicated on the idea that values can have an infinite set of ranges, that there can be any amount of gravity, as little as you like, as much as you like, just like there is force and mass and whatever. But quantum mechanics is predicated on the fact that everything comes to be, everything exists in discrete states, not the numbers in between. And so while one branch succeeds to tell us about 75% of the universe accurately, another branch tells us what the missing 25% is very accurately. And the fundamental math that drives both of them is so different that there can be no reconciliation in between these two kinds of physics, at least as we understand it now. Now, that probably won't hold us for very long, but right now that is basically the state of physics. In any case, I hope you've enjoyed your last lecture and this course. I'll see you again soon.